This video is to help you with the classwork for section 7.1.1. The section is on distance, rate, and time. And our learning target is to make tables, graphs, and rules relating distance to time for objects traveling at a constant rate, and to determine the relationship between distance, rate, and time. So it says in this course you've looked at several relationships between two sets of information and investigated how one piece of information can or cannot be found from another. To continue our investigation of proportional relationships from Chapter 4, we're going to look at the mathematical relationship between distance, rate, and time. Later in the final section of this chapter, we'll identify proportional relationships and use our understanding of proportionality to solve problems. So it says, if you needed to predict how far a train, car, or plane had gone, it'd be helpful to know something about how fast it was going and how long it had been moving. So the idea is to find the relationship between distance, rate, and time. Now, we are not going to worry about the experiment that they have indicated here. So what we are going to do instead is to move to problem 7.3. All right. So if we knew, for instance, that in this case, toy car was traveling for 60 seconds and that it traveled 3.5 meters, we should be able to figure out its rate. All right, so if we know that in 60 seconds it went 3.5 meters, you could even extend that to a table and say, all right, then we know that in 120 seconds, in other words, 2 minutes, it would go twice as far, so 7 meters, because they are assuming that this is at a constant rate. You could also expand your table and say, okay, we know then that in 30 seconds, which would be half as long, it would go half as many meters. Half of 3.5 is 1 75/100. So if you were trying to look for a table, you could take your data and create a table with some additional points based on the fact that we know that this is a constant rate. If we were going to graph this, what we would see is that it was going to start at 0, 0, because at 0 seconds, it will go 0 meters. And we would also see that it would be linear, because again, that constant rate creates a linear proportional relationship. Okay. So what you want to say for 7.3 to put into your notebook is go ahead and put in the values that I have, and then basically that it would go through 0, 0 on a graph, and it would be linear. And again, that's because it's proportional. Remember from Unit 4 that the qualities that make a situation proportional is that it does go through 0, 0, and it does have a constant of proportionality and then create a linear graph. Now, for 7.4, the idea is how can we write an equation that relates the time that it's been moving to the distance it traveled? So what we want to do is to recognize that if we were going to create a equation, that distance that the car travels would be equal to its rate times the time that it traveled. And I'm using the x for multiplication. I could also use a raised dot. Okay. So then when we are going to look at putting in specifics, we could put in the distance, 3.5 meters, put in the time, 60 seconds, and solve to get the rate. Right? That would basically be an algebraic equation, and we could then solve specifically for this car. All right? But let's look at 7.5. If our toy was twice as fast, how far would it travel each second? Well, it would travel twice as fast, so twice as far. So that time in 60 seconds Instead of going 3.5 meters, it would go 7 meters. In 120 seconds, instead of going 7 meters, it would go 14 meters, and so forth. So we would see this distance being doubled in our table. All right. So in the table, if rate or speed is doubled, the distance is doubled. And then how would we see that in the graph? Well, in the graph, it would still go through 0, 0, because 0 seconds, it would travel 0 distance, no matter how fast it goes. If it doesn't travel any seconds, it won't travel any distance. So it would still go through 0, 0. It would still be linear. But the difference is that it would be more steep. The line would be more steep. We know from what we've done in 6th grade and in 7th grade that the higher that rate or constant of proportionality is, the more steep the line is. All right, so this is what you should copy down for 7.5. Again, pause the video whenever you need to copy this information down. And then it says if your toy travels at a constant speed, then the distance your toy has traveled and the time it has taken are related to each other proportionally. So again, in a proportional relationship, two quantities are related by a constant of proportionality, or we call it a constant multiplier. And in this case, the constant of proportion is the rate, or we can call it the speed. We've seen other examples where we've worked with a constant multiplier, where we've worked with a constant of proportionality, but we don't need to write those down. So now what they want us to do is to answer questions based on what they've given us. What distance would our toy travel in 9 seconds? How far would it travel in 25 seconds? How many seconds would it take your toy to travel 300 centimeters? So again, even though you could use a table or a graph, the most precise way to get this information is to use an equation or a formula. And we know the distance equals the rate or speed times the time. And again, I'll put a raised dot in for multiplication. So we know, based on what we've said here, that in 60 seconds it went 3.5 meters. So 3.5 meters, or we could change that to centimeters, which we'll need down the road. We're trying to find the rate, and we know that that happened in 60 seconds. So our time is 60. So what we have is 3.5 meters equals the rate times 60, or I can rewrite this as 3.5, we don't really need the label, equals 60 R. R is going to stand for rate. And remember that multiplication is commutative, so we can change the order without changing the answer. So 3.5 equals 60 times R. Now, we know how to solve this equation. This is an algebraic equation. This would be sort of our last step where we get to the point where we have a number equal to a coefficient times a variable. And we know that the way to solve that is to divide by the coefficient. In other words, in this case, to divide by 60. Remember, you want to divide by 60 because we want the value of 1R. And so then when we take our 3.5 divided by 60, it might throw you off because we've got a smaller value divided by a larger value, but that can happen. We're getting a rate of 0.0583 repeating. And that would equal our rate. We could also, especially if we were using a calculator, scientific calculator, we could change that to a fraction, which would be a more specific answer. Once you've created your equation, and once we found the rate, we now have an equation. The situation for this problem is that distance would equal that rate that we just found, 0.0583 repeating, times the time. Now we can put in the information that we're given. So we can put in 9 seconds for time and see what distance we get. We can put in 25 seconds for time and see what distance we get. And we could put in 300 centimeters for distance and see what time we get. Now, the thing to keep in mind is, again, this is in centimeters and this is currently in meters per second specifically. So we want to be clear on that. We have found our rate in meters per second. The label is important in this case. Okay. So if we put 9 seconds in, then we would say distance equals, again, that constant multiplier that we just found, times 9. I'm going to put my repeating bar over that as well. So I'm going to take this rate that I just found, times 9. And I'll find that it would go 525 thousandths meters in 9 seconds. Okay. Then for 25 seconds, again, I'm going to write down the equation, distance equals rate times time, using the rate that we found. And this time I'm going to replace time with 25, because that's how many seconds we were told to use. So again, you can use a calculator throughout this whole unit. So I'm going to take that constant multiplier, which again was this, and multiply it now by 25. So we get, looks like 1.4583 repeating. And again, that happens oftentimes when you work with real numbers. You don't get numbers that necessarily come out so nicely. That's okay. So make sure I copied that correctly. Yep, looks like I did. And then for this last one, if we want to know how many seconds it would take our toy to travel 300 centimeters, first we'd have to change 300 centimeters to meters. Because again, remember that our rate is in meters per second. So we are either going to have to change our rate to centimeters or change our centimeters to meters. Got to change them so that we're comparing apples to apples, not apples to oranges. So remember, the way to change from centimeters to meters, since there are basically 100 centimeters in a meter, is to move your decimal 2 places to the left. So in other words, 300 centimeters is 3 meters. Now we can write down our formula again, which was distance equals rate times time. Our rate was that value. And put in my repeating bar. Oops, I forgot a 0 here. I need to have that. Okay. And then in this case, instead of putting the time in, I'm given the distance, specifically 3 meters. So I'm going to say 3 equals this value. Again, we're at the point where we're solving a algebraic equation where we have a number on this side. We have this multiplier times our variable. How do we get the variable by itself? We divide. The variable is currently being multiplied by that. The opposite is to divide, or inverse is to divide by that. And again, we're going to do it to both sides. When we do it to the left side, we will get our answer, and when we do it to the right side, we'll get just t, which is what we want. So we'll put in our calculator, 3 divided by that value. And we get 51 point, and it's kind of an ugly decimal. This is why we typically want to work with fractions, because they're a little more precise. But for today, since this calculator at least, that's decimals, we'll go with that. Our time would be approximately 51.5 seconds, or 51 and 428,572 millions. All right, and again, that's in seconds because time is in seconds. So again, copy what you need to from this for your classwork. We will not worry about 7.8 or 7.9, although you can do those for extra credit, and then we'll have a separate video for your homework. Thanks.